Hi everyone. In this video, we're going to be talking about section 1.2, the definite integral. In the last section, when we were computing Riemann sums, we had the restriction that f was non-negative and continuous. Well, in this section, we're going to try to lift those restrictions on the function f. So let's say we have a function f that isn't necessarily non-negative. So in this graph, I've drawn a function y equals f of x, and we can see that this function is not non-negative because it dips below the x-axis. So as per usual, if we were going to compute an approximation for the area under the curve, we would partition like so. And then we're going to pretend that these are evenly spaced. And if we look over to the right here at the Riemann sum that I've written, I have f of xi, so we're going to use a right endpoint approximation. So to do that, let's draw the rectangles. Now, what is the Riemann sum saying? Well, when we take f of xi, then that's giving us the height of each rectangle. So when we're talking about the red rectangles, our heights are positive. But what happens when we talk about the blue rectangles? Well, those heights are actually negative. So when we do our approximation, we end up computing the areas of these rectangles. And then when we compute the areas of these rectangles, they actually come out to be negative. So when we actually do the computation of this Riemann sum, we'll get the areas of the red rectangles, and then we will be subtracting off the areas of the blue rectangles. Now, as we noted earlier, when we put infinitely many rectangles underneath this curve, by taking a limit as n goes to infinity, well, the areas underneath end up smoothing out. So we have something like so in this graph here. It's supposed to be a graph of the same function. Well, what ends up happening when we compute the area under the curve, which is the limit of the Riemann sum, well, that just ends up being a1 minus a2. Now, when we have a function f, then we denote by this curly s, the integral symbol, from a to b of f of x dx. This is what we use to denote this limit as n goes to infinity. Now, if this limit does exist, then we say that f is integrable on AB. So that's if the limit exists. Now this A and B we call the limits of integration. Now be careful here, we don't want to get that confused with the limit of our sum. Those are two different things. The function f is called the integrand, and this dx just denotes that f is a function of x. So we call this the definite integral, and we use the definite integral to compute the area underneath the curve. But when the curve is not necessarily non-negative, then we end up getting the area above the x-axis minus the area below the x-axis, and that's called the net signed area. One thing to be careful of is that if we're computing the definite integral of f of x dx, well, that's the same thing as that of f of u du, and the same thing as that of f of a cherry d cherry. The variable of integration does not matter. So what can we do with the definite integral? Well, the definite integral has some very nice properties. So we can reverse the limits of integration. That's what property 1 is saying. We could pull out constants, which is property 2. we can distribute the integral over sums and differences. And whenever we have some variable, some number c that lies between a and b, well, we can actually split the integral up from a to c and then from c to b. This should look eerily similar to what we did in using the sigma notation when we were able to split up sums. So this is very useful because if we know like the value of an integral, well, then we can actually use that to compute the value of other integrals using these algebraic properties. Now, something else is that definite integrals preserve information about the function. So let's say f is bigger than or equal to 0 on AB. Well then, so is the integral, the definite integral from a to b of f of x dx. We can use these properties that the definite integral preserves about the function to compare functions and even find upper and lower bounds for the integral. And maybe the most important thing is that the definite integral can be used to find the average value of a function, which you will encounter in your reading. So I hope this video helped, and thank you for watching.